Hello. So recently I spent some time over two videos thinking through a proof of compound angles, I should say a particular proof of compound angles, because there are many variations in different approaches. And you can see the working here, or go back and review those videos where it was proven that cos alpha minus beta equals cos alpha cos beta plus sine alpha sine beta. And likewise, we've got our other identity, cos alpha plus beta equals cos alpha cos beta minus sine alpha sine beta. And we've got our sine sum and difference identities down here as well. Now, what I want to talk about in this video is just, I suppose I want to think about another variation of this proof. And I'm not going to work through the entire thing. I'm just going to work to the point of proving again, like I did in the other proof, cos alpha minus beta equals cos alpha cos beta plus sine alpha sine beta. And because from that point, one can just expand if they want, and they can prove all the other identities based on that result. So I'm not going to go through the whole thing. I'm just going to prove cos alpha minus beta equals all of this, and one can expand on it if you wish. And I suppose that if one wishes, and I suppose the purpose is just to compare, because this is a cool method. It's a completely different approach. It's quite different, I would say, in as much that there are similarities, because ultimately we are dealing with the same things, the same concepts, more or less. And so in this proof, so let's just say, so to start, one's going to want to prove cos alpha minus beta equals cos alpha cos beta plus sine alpha sine beta, right? And so what wants to do is essentially consider two separate angles, alpha and beta, and then we want to find the distance, which I'll denote as d, well, how about I just draw them first? Okay, so we want to draw two unit circles. I think this is how to do it. I've never worked through this proof before, but I know it exists, and I know that it's very similar to the other one, except in this case we want to draw an entire unit circle. So this proof again relies on the unit circle, and it relies on no geometry. Well, it's not so geometrically inclined, let's say. In terms of some of the other proofs, like where you essentially are just working through geometry. Literally, you don't even deal with a lot of algebra to prove these identities. Okay, and so we've got one unit circle. We want to draw a second unit circle, and the reason for that I will just explain in a moment. So I'm just going to try my best to draw a circle. I'm not very gifted when it comes to drawing things like this, but that should be more than sufficient. So we're going to draw, let's start in this unit circle, let's draw our angle alpha. So we want to have basically two radii, like so. Right, this is length 1, we know, according to the unit circle definition. And this entire angle, like this, we're going to call that alpha. So this is alpha, angle alpha. Maybe I'll use a separate color. This is angle alpha, this entire thing. Now angle beta is going to be this angle right here. We're going to call that beta. And so what's really interesting about this, and in fact actually I'm not quite done with this diagram. We need to complete this. We're going to draw a chord right across. Now we have our triangle, and we're going to label this side D. You can label it anything you want, but it's not so arbitrary if we just label it D, because we want to find the distance of this side. That's crucial to this proof. So we've got this set up. We can label the points now. The point here, this point right here, do I need to color it? Probably not. This point, we have cos alpha, cos alpha, this is cos alpha sine alpha. So again, very similar to the proof in the other video in terms of the points that we're labeling it. It's the coordinates, you'd say. This coordinates of this point are going to be cos beta sine beta. Right? Because we're just working on these angles, essentially. So we can label, we know that the coordinates of this point are cos alpha, this is sine alpha. We know the coordinates of this point are cos beta, sine beta. Now let's just focus on the second unit circle here. And we're going to draw another triangle, radii, or radius in this case, just up. We know that's 1. Again, unit circle definition, think of Pythagoras identity, however you want to think about why that's length 1. And we're going to draw a chord now, down with the coordinate axes, straight down, or not quite straight down, but you can see here. Now this angle, right here, we're going to call this alpha minus beta. And this distance, let's just label this d. And now we can establish our coordinates for here. Well, the coordinates for this point right here, well, we already know what that's just 1, 0, right? Just think of the unit circle. That's all that is. The coordinates of this point, however, are quite curious. They are, let's just think about it. This is angle alpha minus beta. It's going to be cos alpha minus beta, close the brackets, sine alpha minus beta. And so one might say, well, okay, we've just drawn 2 unit circles. We can easily discern the coordinates of these points. That takes no time at all, no problem. But where does this lead us? We just have 2 unit circles. They don't really seem attached at all or anything. Well, what's really interesting about this proof is that the distance d in both cases, so let me put that very explicitly, the distance d in the 2 unit circles are equal. They are equal. And thinking about that is actually really quite interesting. But they are equal. And from that assumption, which is true, right, we can certainly determine that it's to be true, we can then obtain from the first, let's just, should I denote this? Let's just call this 1, okay? Unit circle 1, unit circle 2. From unit circle 1, we can obtain that the distance equals, and again, we're just using distance formula, not so dissimilar to what I did in the original proof that I discussed at the outset of this video. So the distance formula, right? It's x sub 2 minus x sub 1, y sub 2 minus y sub 1. Well, what is x sub 2? Cos alpha. Cos alpha minus x sub 1, cos beta. And one might see a pattern emerging actually between these steps now and what I did actually in the initial proof, which is also cool. And of course this is y sub 2, so sine alpha. Again, this is just distance formula. It's very simple, very basic. Sine beta. And we're squaring that. That's all under the square root sine. And for unit circle 2, go like this. Unit circle 2, we can obtain that d, the distance d, such as right here, equals, I'll put it all under square roots, try to keep it as neat as possible. Well, x sub 2 minus x sub 1. What is x sub 2? Cos alpha minus beta minus 1. Right? Because our x sub 1 coordinate is just 1. So minus 1. Now, what about our y sub 2? Our y sub 2 is sine. So it's going to be plus sine. Actually, I'll put it, and that's squared, of course. Both of these have been squared. Good. So sine alpha minus beta minus. And what's our y sub 1 coordinate? Well, it's not, right? It's 0. So minus 0. And all that's squared. And so let me just clean this up. Try to have everything neat and organized. Okay, so we've got expressions for d of this distance. Okay, we know the length of this side, and in this case we know the length of this side. Likewise here, we know the lengths, the two radii. It's fine. We've got our unknown side, d. Okay. What's really cool about this, though, is that let's just beginning on the assumption that d in both cases is equal. How would I write that? D equals d. Well, let's scroll down just a little bit. We can say, on the basis of that, d squared equals d squared. And from these two expressions for d, if we can deduce that d squared equals d squared, which we can, what does that mean? Well, let's have a look. Because ultimately what we end up with here, if we take d squared, so just to think, okay, we square d here from both cases, square d, what happens? The square root cancels, right? And what we end up with is everything underneath the square root sign as it is squared. And so let's think for unit circle 1, d squared is therefore going to equal, and I'll write it over here for the sake of saving space, cos alpha minus cos beta squared plus sine alpha minus sine beta squared, and we're going to set that to equal d squared here, which is going to be cos alpha minus beta minus 1 squared plus did I write that correctly? I did. Sine alpha minus beta minus not 0, so squared. And from this point on is almost essentially the exact same. It's very similar to the process one went through in the original proof, because we're just going to multiply these out, expand them out, I should say. And so what we end up here, we're going to end up with quite a lot. So I'll go right across the screen, I think. We're going to end up with, if we expand this first bracket, let's just start with one bracket at a time. We get cos squared alpha minus 2 cos alpha cos beta plus cos squared beta plus, what's this expand out to? The second bracket? Well, we get sine squared alpha minus 2 sine alpha sine beta and plus sine squared beta I'm not entirely sure this is going to fit. I'll put equals down here, and so let's focus on this bracket. What are we going to get? We're going to get cos squared alpha minus beta cos squared alpha minus beta minus 2 cos alpha minus beta, right? Yes, minus 2 cos alpha minus beta and plus 1, negative 1 squared plus 1 plus, and now for sine, we are going to get sine squared, right? Yeah, sine squared alpha minus beta, and that's it, because the zeros would cancel. So yeah, so that's it for the right hand side, I think. Yes. So how do we simplify all of this mess? Well, let's look if there's anything cancel. Well, we have a sine squared alpha, cos squared alpha on the left. So that's going to give us 1. So let's write that here. The next line, 1, right? Sine squared alpha plus cos squared alpha equals 1. That's just the Pythagorean identity. We've also got a sine squared beta, and we should have another cos squared beta right here. So that's 1. So we get 1 plus 1. What are we left with? Well, just like in the original proof, we're going to be left with, so 1 plus 1 minus 2 cos alpha cos beta minus 2 sine alpha sine beta, and now that's going to be equal to the right hand side, which is which is cos squared alpha minus beta. Is there anything that we can do here? We've got our sine squared alpha minus beta and a cos squared alpha minus beta. And we have a minus 2 cos alpha plus beta. Is there some way to simplify this? That's what I'm trying to discern. That's going to be 1, isn't it? Yeah, okay. These will cancel. Sine squared alpha plus beta. That's going to leave us with 1. We've got a 1 here as well. So let's just trying to think, will this lead us to where we want to go? I think it will. 1 plus 1. I've not worked through this proof before. So we get, sine squared alpha minus beta plus cos squared alpha minus beta, right? We have that. These will cancel to give us 1. We've got another 1 here. That's 1 plus 1 minus 2. And we're left with cos alpha minus beta. And so therefore we're left with 2 minus 2 cos alpha minus beta. Yeah, this is going to work. We're exactly where we want to be. 1 plus 1 is 2 here. So we can cancel things out on both sides. If we subtract 2 from both sides, it's going to cancel. And if we divide by 2, or we can factor out a negative 2 here. Maybe that's the best approach. Yeah, I think that's what we should do. Factor out a negative 2. Okay, before I cancel anything, I just want to simplify this. Yeah, so we can factor out a 2, so we have 2 minus 2 times, right? I'm just factoring out a 2 from here. We get cos alpha, cos beta, plus, now it's going to be plus sine alpha, sine beta, because this is what we need in our identity. Now we've got a 2 minus 2 cos alpha minus beta, and we can see, if we go back up to the original identity, what we need to prove. We have cos alpha minus beta, so we've got our cos alpha minus beta. We've got cos alpha cos beta plus sine alpha sine beta. We've got that here, cos alpha cos beta plus sine alpha sine beta. So we are on track by factoring out that 2. Now we can cancel, because now we can divide across. So if we subtract this 2, or subtract 2 from both sides, these cancel. If we divide by negative 2 from both sides, that's just 1. So they effectively cancel. And so what we end up with is exactly what we want. And I'll just rearrange it. I'll flip the sides. So it's going to be cos alpha minus beta equals cos alpha cos beta plus sine alpha sine beta, and yeah, we're done. We've proven the identity cos alpha minus beta equals cos alpha cos beta plus sine alpha sine beta. And what's really cool with this, just like in the original proof, now one could invoke the symmetry identity that one could then go on to prove, if you wanted, cos alpha plus cos beta equals cos alpha cos beta minus sine alpha sine beta by invoking the symmetry identity cos negative theta equals cos theta. In other words, you would substitute in for beta, negative beta, double negative becomes positive, you get cos alpha plus beta, and then the sine, negative sine beta, because sine is an odd function, that comes out, and then you get your second identity. And you effectively would carry out the exact same process as in the original proof that I did, where we see right here, we proved cos alpha minus beta, then we went on to prove cos alpha plus beta by, again, invoking the symmetry identity. You can see that right here and right here. And then we went on to invoke cofunction identities right here to prove sine alpha plus beta, and on and on and on. And you would do the exact same thing from this point in this proof, from this point forward. So it's kind of cool just to think that these two lengths are the same, d and d, and from that we can say we can come up with a formula using distance formula for d, for unit circle 1 and unit circle 2, and we can say, well, d is equal to d squared is going to equal to d, and therefore they cancel, and you go through all of this, and yeah, so that's a slight variation on the original proof.